on His Majesty's service. Vestibular receptors. The vestibular system performs important sensory functions, providing the perception of head position, self-motion, balance, spatial orientation. It also takes part in stabilizing gaze during head movements and posture. The peripheral part of the vestibular system includes two types of sensors, namely two otolith organs, the saccule and utricle, which sense linear accelerations, that is, gravity and translational movements, and three semicircular ducts, which sense angular accelerations in three planes. This sensory information is reported to integrative centers in the brainstem, cerebellum, and somatic sensory cortices. Sensory elements in the vestibular system are represented by hair cells, which are similar to those of the spiral organ. The difference is that unlike cochlear hair cells, vestibular hair cells, in addition to stereocilia from 30 to 150, contain one kinocilium. The latter is a modified cilium containing 9 pairs of the peripheral and 1 pair of central microtubules. Kinocilium is taller than stereocilia and has a club-like extension at the end. Two types of vestibular hair cells are distinguished. The type 1 vestibular hair cells are similar to the inner hair cells of the spiral organ. The type 2 vestibular hair cells are similar to the outer hair cells. Round bases of type 1 vestibular hair cells are surrounded by calyx-shaped sensory nerve endings. Those of type 2 vestibular hair cells are bud-shaped. The vestibular hair cells are responsible for the mechano-electrical transduction process. The mode of transduction operated by these cells is also similar to that of the cochlear hair cells. Endolymph flow in the vestibular part of the membranous labyrinth, resulting from head movements, creates shearing force. When it leads to deflection of the hair bundle towards the kinocilium, mechano-electrical transduction channels at the apices of the hair cells open and depolarization of the hair cell takes place. Deflection of the bundle in the direction of its shortest stereocilium leads to closure of mechano-electrical transduction channels and to the hair cell hyperpolarization. It is worth noting that some mechano-electrical transduction channels are open in the absence of stimulation, which triggers continuous generation of receptor potentials and release of glutamate by the hair cells in a tonic manner. In the case of depolarization, more voltage-gated calcium channels at the ribbon synapses are activated, leading to the release of more glutamate into the synaptic cleft. Glutamate molecules bind to the receptors on the postsynaptic membrane of the vestibular nerve fibers endings and generate action potentials, resulting in an increase in the firing rate. In the case of hyperpolarization, less voltage-gated calcium channels are activated, which leads to the release of less glutamate into the synaptic cleft and reduces the activity of the vestibular nerve. Thus, the firing rates of vestibular fibers increase or decrease, being similar to the receptor potentials of the hair cells. The hair cells of the utricle and saccule are housed in the maculae, formed by thickenings of epithelium in these parts of the membranous labyrinth. the hair cells are surrounded by supporting cells and form tight junctions with them. Thus, endolymphatic and paralymphatic compartments are divided, as in the spiral organ, and endolymph does not mix with paralymph. It is estimated that the macula of the human sacule contains about 18,000 and the macula of the utricle about 33,000 hair cells. The surfaces of the maculae are covered with a gelatinous coating, the otolith membrane, into which the kinocilia and stereocilia of hair cells extend. The otolith membrane is covered with the so-called statoconia or otoliths. In Greek, otolith means ear stone. They are built of calcium carbonate crystals. Vestibular hair cells of the utricle and sacule are characterized by polarization relative to the so-called streola, which divides the maculae into two opposite groups. In the streola, the otoliths are very small, and the thickness of the otolith membrane is either reduced in the utricular macula or increased in the saccular macula. The cells of the utricular macula are polarized so that the kinocilium is always on the side toward the streola. Conversely, the kinocilia of the saccular hair cells are oriented on the side away from the streola. Note that in an upright individual, the macula of the sacule is oriented in a plane close to the vertical, and the macula of the utricle in a plane close to the horizontal. In this posture, the sacule responds to movements of the head in the vertical plane, up-down, and forward-backward movements. The utricle responds to movements in the horizontal plane, lateral displacements, sideways head tilts, as well as anterior-posterior motion. Thus, there are only two sensory organs for three axes of linear motion. However, they can respond to movements in all three dimensions. The otoliths make the otolith membrane about 3 times as dense as the surrounding endolymph. With the head erect, the otolith membrane bears directly down on the hair cells, and stimulation of the vestibular nerve is minimal. When the head tilts, gravity causes the membrane to shift relative to the hair cells. The shear motion between the otolith membrane and the macula displaces the hair bundles, and receptor potential is generated. The shear motion between the otolith membrane and the macula also occurs when the head undergoes linear accelerations. The greater relative mass of the otolith membrane causes it to lag behind the macula temporarily, leading to the transient displacement of the hair bundle. Every movement triggers depolarization in the group of hair cells from one side of the streola and simultaneously hyperpolarization of the hair cells from the other side. Besides this, the saccular and utricular maculae on one side of the head are mirror images of those on the other side. Thus, a tilt of the head to one side has opposite effects on corresponding hair cells of both the utricular or saccular maculae. Any movement of the head causes a combination of inputs from the utricles and saccules of two ears. The brain interprets head orientation by comparing inputs from otolith organs to each other and to inputs from the eyes and proprioceptors in the neck muscles. Each ampulla of the semicircular duct contains a crista ampullaris, which is a thickened transverse epithelial ridge that is oriented perpendicularly to the long axis of the semicircular duct and consists of the vestibular hair cells surrounded by supporting cells and forming tight junctions with them. Type 1 vestibular hair cells are concentrated in the central region of the crista, and type 2 vestibular hair cells are more numerous in the peripheral areas. The apical part of the hair cells is covered with a gelatinous ampullary cupula, which has the shape of a bell without a cavity. It forms a fluid-tight partition that has the same density as that of endolymph. The ampullary cupula and the otolith membrane are the products of the secretory activity of the supporting cells. Unlike the saccular and utricular maculae, all hair cells in the crista are polarized with their kinocilia pointing in the same direction. In the crista of the lateral or horizontal semicircular duct, the kinocilia are located on the sides of the hair cells that are closest to the utricle. In the other two ducts, the kinocilia are located on the sides of the hair cells furthest from the utricle. In the case of rotational movement of the head in the plane of the corresponding semicircular duct, its walls move, but the endolymph lags behind due to inertia. It causes displacement of the cupula in the direction opposite to the direction of rotation and deflection of the hair bundle. If a constant speed of rotation is achieved, the endolymph moves at the same speed as the walls of the semicircular duct, and the cupula returns to its original position. As the speed of rotation decreases, the cupula moves again under the action of the endolymph, which continues to move at a higher speed than the head. The deflection of the hair bundles, same as in the hair cells of the utricular and saccular maculae, leads to their de- or hyperpolarization and generation of nerve impulses in the vestibular nerve. It was noted all hair cells in the cristae are polarized with their kinocilia pointing in the same direction, but cristae on one side of the head are mirror images of those on the other side. Thus, each semicircular duct has a counterpart with its hair cells aligned oppositely. Each of three pairs of semicircular ducts works in a push-pull fashion. When the hair cell in one duct is depolarized, the hair cell in its corresponding partner on the other side is hyperpolarized. This push-pull system makes it possible to sense all directions of rotation and transduce receptor potentials into nerve impulses perceived by the brain. Afferent nerve fibers of the vestibular nerve can be divided into three types. Some nerve fibers have pure calyx-shaped terminals which innervate type 1 vestibular hair cells. Some nerve fibers form pure bud-shaped or Boughton afferents innervating type 2 vestibular hair cells. One nerve fiber innervates several, up to 10 cells. The remaining nerve fibers have dimorphic terminals innervating both type 1 and type 2 vestibular hair cells. Vestibular hair cells are also innervated by efferent nerve fibers originating in the brainstem and reaching the inner ear within the vestibular nerve. They form terminals on the calyx-shaped endings type II vestibular hair cells and their Boughton terminals. It was shown that efferent nerve fibers play an important role in adjusting the resting firing rate of afferent nerve fibers that encode rapid head movements and are required for normal vestibular adaptation and compensation. This supports the notion that otolith organs and semicircular ducts are not passive transducers of head movements, and their sensory signal transmission is modulated by efferent inputs. Thank you for attention.